There's another thing that I wanted to mention having to do with positron emission tomography. This one is not in your book, but it's another interesting compound that I became aware of a couple of years ago, the first time I had seen it. I'm particularly interested in this compound because a lot of members of my family have, a number of members of my family have developed Alzheimer's disease, and this is something that shows very, very good promise, at least for diagnosing the condition. It used to be that when someone had Alzheimer's disease, the only way that you could actually determine that, in fact, they did have Alzheimer's disease was a post-mortem. That is, after the person died, you could autopsy the brain, and you would see in the brain of someone that was affected by Alzheimer's disease, you would see what are known as beta amyloid plaque, sort of a whitish plaque that forms around particular areas of the brain that are involved in cognition. And you also saw what were called tau tangles. So these are two probably misfolded proteins, or proteins that do occur normally in the body, but it turns out that we don't see them in normal brains. We don't see them accumulated. And it's not really understood whether these things are causing the disease or they just may be symptoms of the disease. But nevertheless, this is a way to diagnose the disease, because you can actually make this compound. It's called Pittsburgh. It's referred to as PIB, which actually just stands for Pittsburgh. It's developed at the University of Pittsburgh, so it's Pittsburgh compound B. And Pittsburgh compound B, although this kind of a compound is called a benzothiazole, and this particular benzothiazole actually is it's a relatively small molecule. It passes through the blood-brain barrier. It turns out that molecules, if they're too large, they're actually filtered out. They're not actually able to enter the brain. So it's difficult sometimes for certain kinds of drugs to actually get them to go to the brain, because it's kind of a mechanism for preventing bacteria from getting to the brain, and certain other fairly, although small from our perspective, at least in terms of a molecular perspective, fairly large macromolecules that might damage the brain. So the brain has developed this system of capillaries that actually filter out some of the larger molecules. But this plant passes the blood-brain barrier and actually is selectively adsorbed onto the surface of this beta amyloid plaque. So this molecule in itself wouldn't do anything, but it turns out that we can easily label this carbon atom right here, this methyl group, CH3. This is called a methylamino group, and we can label this carbon atom with carbon 11, which is a positron emitter. And then again, we've got that three-dimensional way of looking at the brain. And the nice thing about that is that in the future, when there are compounds that will perhaps actually do something to shrink the amount of beta amyloid plaque, this would be something that you could visualize without having to cut someone's head open and see what was going on inside. You'd actually be able to get a visual image of the plaque reduction. And perhaps you could even see that someone was being cured, not just because they were experiencing less cognitive problems, but you could certainly, but because you saw less plaque, or at least you could see that if you were giving a drug that while it didn't remove the plaque, at least it prevented more plaque from forming, then using this as a diagnostic agent to find this at very, very early stages of Alzheimer's might help people lead a higher quality of life for a longer period of time. Okay, and tracers have a lot of other uses. I'm not going to go into all of them. There's one other one that I wanted to actually see if I can find this. I had one other one that I did want to briefly talk about. But tracers are used in things like hydrology. We already mentioned the medical diagnostic use of tracers. They're used in something. They're used in biology a lot. They're used for what is known as a radioimmunoassay, where basically you take it's an antigen-antibody reaction, and you have an antigen something that you're actually interested in looking at that would bind to an antibody, and you could have a radioactively labeled antigen, and that binds to an antibody. And then if you want to actually assay for the presence of the antigen, you basically put the antigen into this mixture, and the antigen, some of this antigen will replace the radioactive antigen, which is then not bound anymore, and it's possible to actually determine from the amount of radioactivity that you now have in solution how much of this non-radioactive material was actually present in your sample, in your analytical sample, because this is going to knock some of this out, and then this free AG, the antigen, will actually be able to quantitate that. So that's another technique. And for me, as an organic chemist, I find this is also very, very useful for things like elucidating or finding out the mechanism of a chemical reaction. So here's one I wanted to talk to you about. There's a compound that actually has some biological importance. It's something called mandelic acid. And you can prepare this by the alkaline hydrolysis. That is, you put it in with some base, some strong base like sodium hydroxide or potassium hydroxide. And you can hydrolyze a compound called phenyl glyoxal. So this group here is a phenyl group. These are actually carbon atoms, 1, 2, 3, 4, 5, 6 carbon atoms, and then there are hydrogens around here and other groups attached to it. But if you have just, I'm going to erase this here, and if you have just the phenyl group here, I'd like to abbreviate this now so we don't have to keep writing it out. It's sometimes abbreviated PH, and it can also be abbreviated with the Greek letter phi. So I'm just going to use phi to represent this so I don't have to keep drawing the group over and over again. But if we have this chemical compound, which is called phenyl glyoxal, and we treat this with a base, what's going to happen is, and this is important for organic chemists, we want to know what we call the mechanism of this reaction. In other words, how does it take place? Because we can get to the same product in one of two ways. It's possible either that the OH group is going to add to this carbon here, or it may add to this carbon here. And the question is, which one does it add to? So if it adds to this carbon here, what's going to happen is it's going to form something that looks like this. And then we have the possibility, we've got a couple possibilities once that happens. So if it adds, depending on whether it adds one way or the other way, we're going to get one of two possibilities. So one of them, if we actually start out by taking our phenyl glyoxal and we label it, we won't use carbon 11 now, we'll use something like carbon 14, which is a lot easier to obtain, but we can actually put a carbon 14 atom right here, so I'll use the asterisk to indicate that that's a radioactive carbon atom. We put that in there, and then we actually add OH to that, and we can get, as I said, we can get this, we can get this, or if it goes the other way, then we could get something that looks like, it's going to look like this. It's going to be OH, O minus C, CO, OH. And then there's a possibility, there's two possible things that can actually happen, depending on which one of these two compounds that we actually get. So one is that this hydrogen group here can migrate or actually move over to this carbon, and the other, in one case. And in the other case, we can have this phenyl group actually migrating and moving over to this carbon. Well, they both give you the same chemical compound, but the difference is if the phenyl group, if the hydrogen migrates, let's see, this is the one where I was having the phenyl group migrate. Here's the one where the hydrogen was migrating. If the hydrogen migrates, what you actually wind up getting is something that looks like this. Phenyl, CH, here's the carbon 14, it's right here, CO2H, OH, And if it's the other way, over here, where the phenyl group migrates, what you're going to get is the same chemical compound, but now the radioactive carbon is not going to be on this side, it's going to be on this side, it's going to be over where the CO2H is, OH. And if you heat both of these things up, they both will give you this compound, which is called benzyl alcohol, plus carbon dioxide. So it's very, very easy to find out which is the correct mechanism when you do this, because there's only these, well, there's actually three possibilities. Possibility is that both hydrogen and the phenyl group migrate, in which case you would get a mixture. But if it's all of one and none of the other, then you would either get radioactive carbon dioxide, or you'll get radioactive benzyl alcohol, where the radioactivity is at this carbon here. And it turns out that when this study was actually done, there was no radioactive carbon dioxide that was produced, and the only thing that was found was radioactive benzyl alcohol, and that indicates that it is actually the hydrogen that's doing the migrating, and not the phenyl group. So this is just a way that we can use this kind of chemistry to demonstrate what the mechanism of a chemical reaction is, and this is very important for chemists. So that pretty much concludes that chapter on nuclear medicine. And the other thing that I wanted to mention then is the idea of radiation therapy and food irradiation. This is the next chapter. And this chapter, actually, historically, if we go back to the discovery of ionizing radiation, X-radiation, it wasn't long after the first X-ray that was actually taken, which was, we've already seen that Henri Becquerel's wife, or was it Rankin's wife? I don't remember now. But one of them actually, I think it was, let's see, who did we say it? This was so long ago that some of you may remember, but I've forgotten now who we actually attributed this to. But the point was that when radioactivity was originally discovered, we actually could see there was an X-ray that was actually taken of this woman's hand, and that was back in the very late 1890s. So, but in terms of actually using X radiation for therapeutic purposes, that is to actually treat something, that's still been going on for a very long period of time, and we actually have, I think the first time X radiation was actually used to treat cancer was back around 1905. So it's been used for over 100 years now. And once Marie Curie had actually isolated radium, then there was a lot of work that was being done using even radium and some other radioactive materials that could also be used to treat cancer. Radium itself was not used, but the radium emanation, the radon that was given off when radium decayed, this radon could actually be captured and put into little glass, very small glass spheres, or put into actually little metal capsules that were called seeds, and these seeds could actually be implanted surgically at a particular site where they would directly irradiate tissue with gamma radiation from that particular site. It's not used so much anymore because we have better ways of delivering very precise amounts of radioactivity. But this was used for really for a number of years, and I guess it's still probably used to some extent. But now with what is known as isocentric therapy, we can actually find if a tumor is inside someone's body and is at some particular location, we can actually aim a particle beam from a number of different angles and different planes of the body, and we can actually get at the point where this beam would intersect right at the tumor. All three of these beams would intersect there. We can actually focus this at that particular site, and we can deliver radioactivity directly to the site. So there have been, we used 1.33 MeV gamma rays from 1.17 MeV gamma rays from cobalt-60 to irradiate tumors. Now there are actually LINACs, small linear accelerators that can deliver greater than 1 MeV X-rays, and these can even be moved to a hospital room, so it's possible to generate the energies that are necessary for doing this kind of thing. The use of this leads me to one other thing that I wanted to talk about, which is that while radioactivity was in its early stages, people found that you could actually treat tumors with this. There was a lot of specious claims that were made for radioactive materials, and there was a point in time when the general population seemed to feel that that radiation could really do no harm, and that it was if a little radiation was good, maybe even more could treat other kinds of conditions that were a little bit more difficult to treat. And because of that, a lot of quackery actually developed around the idea of radioactive use of radioactive materials. So there was one particular thing that I wanted to talk about, which was a man by the name of William Bailey, who called himself Dr. William Bailey. He did not have either an MD or a PhD. He claimed to have been a Harvard graduate. It was true that he went to Harvard, but I think after one semester he actually dropped out of Harvard. And what he was doing was he had managed to get a source of radium salts, small amounts probably of things like radium chloride or radium bromide, probably not highly purified. They were fairly expensive, but you could dissolve them in water and dilute the water down to dilute them down to very, very small concentrations. But still, there'd be enough radioactive material in there that he was selling this radioactive water as a kind of panacea, for whatever ailed you. You could take this stuff and you would feel better. Now, there was a very wealthy industrialist by the name of Eben Byers, who in the late 1920s, he was somebody who was really big on the polo circuit, and I think he was coming home from a polo game one day, and he was on a train in one of the upper berths, and he fell out of his berth, and he injured his arm. So he went to his doctor, and the doctor prescribed this material that was known as Radithor, which was actually one of these waters that probably contained a certain amount of thorium in it, and one of the just as radium will decompose to give radon, thorium from uranium. Thorium will also eventually winds up producing some radon as well. So and it also goes through radium as well. So anyway, he was selling this radioactive water, and Byers, after taking a couple of glasses of it, was so impressed with it, he was telling all of his friends about it, and then they started buying it as well. Byers lived from the time that this accident happened, and he was a relatively young man. This happened around 1927. In 1932, when he died, his entire lower jaw had rotted off from had become highly cancerous, and all the tumors and all the radiation damage from drinking this water. It's estimated that he consumed some 1,400 bottles of this Radithor water. And people were actually selling these kits where you could make your own water. So once this happened, basically the newspapers got a hold of this, and it kind of put the end to people ingesting large amounts of radioactive material. When Byers died, his remains were so radioactive that he actually had to be buried in a lead-lined coffin because he had actually consumed, as I said, 1,400 bottles of this, and probably had a few milligrams of radium bromide actually in his body. Very, very dangerous. Again, therapy using radiation is something that's very, very valuable today. Today we know how to administer it in a safe way. The idea is that we want to administer it in a way that's going to not harm, that's not going to harm healthy tissue, and it's just going to destroy diseased tissue. That's what we're mostly concerned with. And we can do that also by using the proper kind of equipment. And most of the people that were doing this back in the early 30s did not know how to do it. One other use of radiation, which is also in the second chapter, is food irradiation, and not just food, but a lot of consumable products, things that need to be sterilized. If you hit them with enough radiation, we can kill the bacteria and fungi that might be present on them. But you have to remember that you have to go to much, much higher levels of radiation to destroy things like bacteria than you would to actually harm a human being. So if you look at page 197, you'll see a schematic for a food irradiation facility where you've got radioactive material that is in a very, very thick lead-lined and probably concrete-lined building. And you've got something that looks like this. These could be lead-lined walls here. Obviously, the operator is going to be outside of this facility. But basically, you've got a conveyor belt in here, and you can put the food in through the conveyor belt, and it'll run, let's say, down here and over here, and then it runs up here and along here, and it comes out of the conveyor belt here. And of course, it comes out non-radioactive. It goes in non-radioactive, but the whole time it's in here, it's being bombarded by enormous quantities of gamma radiation. This might be cobalt-60 that's in here. So there's a lot of gamma radiation that's actually impinging on whatever's moving around on the belt. But what comes out, as I say, is relatively safe. Now, if you're using this to sterilize things like bandages or things that are just not going to be consumed in the sense of they're not going to be eaten, it's really not a problem to use very, very high doses of radiation. Materials come out non-radioactive. With food, you have some other problems associated with that because basically at these very, very high levels, one of the things that happens is if you have, I'm just going to illustrate this with, let's say, two carbon atoms that are attached together. And this bond, this chemical bond here, is a shared pair of electrons. So if you hit this with a sufficiently hot, energetic, whether it's another electron, a beta particle, or a photon, a gamma photon, something that is sufficiently energetic, probably a gamma photon would do that. This is actually a shared pair of electrons. One of these electrons can actually be knocked, literally knocked out of here, and now we only have a single electron. And this kind of thing, and there's really a positive charge now because we've lost that electron, so we have a net positive charge. And this dot plus sign signifies something that's called a radical cation. And there's really now nothing really to hold these two groups together. So they actually fall apart into one part will actually have will be left with the single electron, and the other one will just be a positively charged, so we'll actually get the cation portion of this, and this is called a free radical. And this is a highly charged species, which could react with a lot of other things, and that's not necessarily good in a biological system. And free radicals are also extremely reactive. They can pull electrons from other compounds. They can disrupt bonds. They can do a lot of damage inside a body. You'll see now you frequently read that some foods are very good scavengers of free radicals. Free radicals seem to promote aging. So these are things that people are trying to remove from their body, not put more free radicals in their body. Although this process could produce free radicals, the concern is not that you would be ingesting free radicals, but when you start breaking bonds like that, if you've got food that you're putting in there, the food could, even though it's not going to undergo bacterial spoilage, it could taste very, very funny if you try to do that because, and they found that, for instance, it says in your book that when they try to do this with meat, the meat would come out with a really bizarre taste. It would taste like burnt hair or something like that. It would have a funny smell to it. So, you know, it seems the process seems to work well with things like dried fruit. There's certain kinds of things that you can put in there where this works pretty well. I've also, although I don't think you'll find this in your book, I've also seen in the past that people have actually used this technique because people, a lot of people like to eat seaweed or products that are derived from seaweed. And one of the problems with taking seaweed flour is that it frequently has that kind of fishy smell to it, but by irradiating it, it seems to cause the smell to dissipate or diminish. So you know, that's another area where this technique could be kind of useful. But the basic thing right now is that you have to overcome people's fear of radiation because you know, the general public will think if it's exposed to radioactivity, it becomes radioactive. Of course, we all know that that's not the case. We're not hitting this with thermal neutrons, so it's not going to make this thing spontaneously radioactive. These are just going to be gamma rays, really, that it's going to be that are going to be impinging on this. And so, you know, it is a technique that has a certain amount of usefulness to it. So that's, I think, pretty much what I wanted to say on these topics, plus whatever else happens to be in the book. We've got two other chapters in here on radiation protection, and then the final chapter on X-ray production, chapter 13. So we're nearing the end, and again, I wish everybody Hatzlacha, and I again thank you for your patience and your indulgence.